All right, let's start with a screen share. Oh, not that. Let's start with this one. Whoops, let me get this in here. Okay, and so let's consider, I think I said let's consider 29.6. And I think this one is a good Biot-Savart law to kind of look at. In theory, you know how to do all of this. However, in practice, there's a few tricks that I might still be able to show you. All right. And so when you consider this loop, you've got n turns. It's in a funky shape. Great, whatever. Everything is indicated in terms of the radius. Okay, so here's a circular segment, half circle. Okay. The magnitude of the magnetic field at the dot is B, and it points out of the page. Determine the direction of current in the loop. I'm going to let you think about that. What do you think? Is the current in the loop clockwise or is it counterclockwise? What do you think?
Counterclockwise?
Counterclockwise.
Yep. And so even though this isn't a circular loop, you could think of it like a circular loop. And so if you grab your hand on that loop, whoops, sorry, let me go to speaker view and make sure I'm up there. So if we have this loop here, and we know that B field at this point right here, we said was out of the page. You could tell that, just pretend it's a circular loop. If you curl your fingers this way in general, that makes sense that we would get a field out of the page. All right, let's just leave that there. Let's call this. I'm almost done. There we go. All right. Which segments produce no contribution? And let's number them. Let me just say 1, 2, 3, 4, 5, 6. Which segments have no contribution?
1 and 5.
1 and 5. They point straight at it, so these two don't matter at all. And so all we have left is to figure out these things. Now, what do you think about 2 and 4? Do you believe that those two are going to produce the same amount of contribution here or not?
Yeah, they should cancel
Yes.
out.
Yeah, because this one's going this way, so it'll be out of the page, and this one's going this way, so it's out of the page. They're the same distance away, the same length. It's totally reasonable. So at first, this looks horrible, and we're like, okay, this one's easy, half a circle. This one is a straight line segment, and then there's this segment here. Now, I'm going to go back and make sure I get the dimensions really quick. We're told that this distance is 2r. Just give me a second while I label it. And then what's this length, this big length here, all the way down of length segment 3?
4R.
4r. Okay, and then I guess this distance here we're told is r, and this distance here is told r. So now I got the picture labeled. All right. Now, you probably realize that straight line segments are the worst because we have to use that mu naught I over 4 pi sine theta crap, right? Do you see any other ways we could simplify this? I can do this problem with one straight line integral or one straight line computation. Do you see how to do that? Isn't this distance 2r? And isn't this distance 2r? If you split this segment up, this, and this all produce the same contribution. They're all perpendicular distance 2r away. They're all length 2r. So we could actually reduce this problem to this. Where we say it was 1, 2, 3, 4. So this thing times 4 plus this thing times 1. Got it? And so what we see here, I don't know if you notice this, on typical physics problems or in loops of wire, it's very common to have some symmetry that you can use to simplify the work. Now, if you don't see this, you would have done possibly 1, 2, 3, 4, 5 integrals and be like, maybe you didn't catch those or 0. Most people catch the zeros, but then you'd still have 1. Well, you'd still, yeah, I don't know. Basically, at some point, if you could catch these things, they'll speed you up. Now, to do these integrals, I know that this one right here is just mu naught I over 2r times 1/2, because it's half of b at the center of a circle. So now I only have one integral to do. So let's figure out this one. Here's my perpendicular bisector. This distance is 2r. This angle is 0 degrees. What's this angle? What's this angle right here? Oh, shit. Sorry. What's this angle right here?
45.
45. So now I don't need to think that hard. It's mu naught I over 4 pi times the distance, which is 2r. Right? So in this case, over here, the distance to the center was r. Over here, the distance is 2r because it was from here to here. So now, and then times sine of 45 minus sine of 0, and I'm done. So something that initially looked really horrible is not too bad, especially if you see that you could just take this contribution and multiply it by 4. I know I didn't do all the details. I'm focused more on the big picture because at some point you need to grind through them. Does that make sense? That setup? Or any questions? I'm going to go ahead and take a quick look at this. Oh, whoops, I closed the, I accidentally closed the.
Wait, I have one question.
Yeah, go for it.
Why is the circle part, why is that equal to 1/2 of the magnetic field?
It's half of the magnetic field of a circle.
Oh, got it.
And the formula for a circle is this. Mu naught I over 2r is the formula for a circle. Since I only have half of it, I take a half of that. So the total magnetic field would be add this to that. Did that make sense?
Yes, that made sense. Thank you.
Got it. Let me get that. Okay, whoops. All right. All right. Let me see here. So I got that, and I'm going to go ahead and do a quick screen share and see if there's anything else on the solution that's worth noting. Zoom. Okay, so all right, so it looks pretty much that stuff, all stuff I pretty much said. You guys got that right. So there we go. By symmetry, you can see I use that symmetry argument right there. I guess I'll say this. Notice in this case, I used a decimal number with mu naught n I over the radius. And so I think you are going to find you like converting these to decimal numbers, especially because there's a Canvas quiz session that says, give me the decimal number that's sitting out in front of mu naught I over r. So there's going to be a problem where you have to basically get the decimal number that's sitting out in front for some weird ass loop. Okay. So you could expect a problem like this where you have to get the decimal number. So I would, when you see me doing the decimal number, do it. Don't leave it in this ugly 2 root 16 pi crap. Okay, so all of these, we're going to have this kind of classic pattern where it's times that factor. Is there anything else? Okay, the largest contribution. Well, yeah, I'll let you do that at home. All right, so let's take a look at the next one. Let's go here. Whoops, to here. All right. This one, if we look at 29.7, when you're looking at this one, all right, let's see what you think. These, I don't know if you noticed a pattern here. One of the things that I've done is instead of calculating B, I make you figure out the current required to create a known B field. This is pretty typical where you might want to know, let's say you know how much B field you need in an experiment, and you have to tell the computer how much current to use. So, so it's common to see this type of thing. So you have 2 wires carrying DC current. I'm going to sketch this up, and let's just see if we can get it started and not do the whole thing, okay? Okay. So we've got this situation right here. You've got 2 wires, one up here and one down here. And I'm going to check one last thing. Okay. Got it. And so to match the color coding in the solutions, this one was a blue one, and this one I used was red. Okay. And I think, what did I call them? I think I called the upper one number 1, just so you know. Just so we're being, not that this stuff matters, but it might make it less time for you later if you want to compare. So I called this wire 1 and this wire 2. All right. What would you do with this? Anybody? What would you start doing? We're trying to figure out the current.
Would rearrange that the DS law to get I.
Okay. I guess like, what do you mean? I'm just trying to figure it out. Or I'm not saying no.
Yeah, B equals mu naught I over 4 pi, right?
Times what?
They're long wires, so it's just the infinite length one.
Exactly. So what does this formula become? That was a good, so he observed, wait, these are infinitely long wires. Remember, these are those wires that go infinitely long out this way and infinitely long out this way. So we're only seeing one slice in the plane, but the wires are actually going forever this way and forever this way. So do you remember how that modifies this formula here?
Over 2 pi A, and A is S in this case.
Okay, is it?
For the first
It's the
part,
distance, it's the distance to the point, right? Along the perpendicular bisector. That's the definition. And I just want to point out, Tom, you're right, it's S, but is this one S?
no, what, root 2 over 2s?
Yeah. Okay. So yeah, exactly. So that's why I was like, I don't want to call it S because S is different for the two, or sorry, A is different for the two wires. Agreed?
Yeah.
All right. Awesome. But you had the right idea there. So now how does that help? Let's let somebody else have a shot at it. This was one piece of the puzzle.
Can we add the equation for the wire for number 2?
So let me see if I understood you right. You are saying B1 equals mu naught I1 divided by 2 pi times square root of 2a. Oh, wait, square root of 2s, I think. And then you were saying just add it to B2, which is equal to mu naught I2 all over 2 pi times just s in this case, right?
Actually, we just subtract it because it's going opposite directions.
Okay, let's pose that. What do you think, class? Does that sound good? Should we add them or subtract them?
A little bit of both.
What do you mean, Trey?
Unfortunately, the magnetic field from the top wire is pointed at a 45-degree angle from the left, down left.
So what you're telling me is it's
Add
a
vectors.
vector. It's a vector. You can't do it this way. You can't just add or subtract. You need to add the vectors first. And then all of you are correct. Nice job. So the whole point of this one was just to remind you, shit, I got to deal with I hat and J hat too. Damn. All right. So if I'm going to add vectors, what's the first thing I usually want to do before I do any math? Starts with D and it's real raw. I'm having a strange day. It starts with D, raw. It's draw. Anyways. Which way do if we don't draw this, you're liable to screw up the components. Trey was drawing it in his mind. Remember, Trey, what way did you say B1 points? Remind me.
Now that I'm drawing it, it's in the opposite direction of what I said.
So that's why you draw it. And so, but I've already forgotten which way, so you could have fooled me. Just tell me which way I got to draw B1.
B1 is at positive 45 from the x-axis.
So here's radius 1. Right? Thumb in the direction of current. There's B1 vector. And then where's 2? Somebody else.
That one's pointing down.
Let me check. Yep. What do you think? And from there, we know this. Trey was saying stick in some sine, cosine 45. Something I always like to check. Do they have the same current or not in this problem? I'm just looking in my book really quick.
They do.
They do? Okay. Gotcha. So in this case, I could then take this away. I got you. And so now when we do this, you put this crap in here, then what? We're going to add these vectors up. So this one's going to be root 2 over 2 in the I hat plus root 2 over 2 in the J hat, if I'm not mistaken. If you don't see this, this is basically cosine 45 and sine 45. And this one is going to be what? Just negative J hat, I think. And the trick is, if you're going to add these, factor out mu naught I over S. So you would factor out mu naught I over S. Immediately grab your calculator, punch in the rest of this crap, and get decimals for it. And then just add the decimals. If you're a math purist, have fun. If you're not a math purist and you want to do a good job and get this done reliably, you should do this. If you're a math purist, you should still do it anyways. Grab the calculator for once. I don't usually say that, But it's just so much nicer to have a simple numerical factor with a single decimal number in the I hat and a single decimal number in the J hat. It's just nicer to do it that way. Not always, but in this case. And then, so all this is going to be equal to some number in the I hat plus some number in the J hat. And this is equal to what? I guess B total. How do I get I?
Can you clarify what you mean by get I?
I need, oh, so remember in this problem, it asked for the current. Let's go look at the word, though. Geez, why does it keep showing this? Let's do that. Then we'll go to this one. We're supposed to determine the current, right? You're going to have a number here, a number there. I'm supposed to solve this for I in terms of mu naught S and what?
I mean, can't you just take the magnitude of your B total and then equate it to B? Easy peasy.
Correct. So the idea is there's one more step. We know that the magnitude is known as B. So I just want to point out basically what you're doing here is this is one of those problems where you know the final answer for the magnitude. So don't overthink it. Go through the same process as usual, solve for the magnitude. Then at that point, once you have found the magnitude by doing this squared plus that squared, square root, then you just say, okay, that is equal to B, and then solve it for I. Nice. All right, good job. Okay, let's try another one. I'm going rapid fire tonight. I had a lot of coffee today, and I'm ready to party. That's all right. Look at this one. This was an old test question. Kicked the crap out of the class that year. I'm going to let you read it for a second and draw it up, okay?
You should put it on the test this year. See how we do.
Be careful what you wish for. This one, I've seen people screw it up even when they have the solutions. So yeah, this one is something about this one, just the geometry messes with people. All right. Dropping markers. Here we go. All right. I'm just going to draw it.
I have a question.
Okay, give me just a sec. Whoops. Yeah, what's up, Tom?
Looking at the straight portions on the left and the right on the bottom, would it work mathematically to do an infinite line one and then subtract out the part that would be the current from the missing chunk?
That's what I was thinking too. That's
correct. And so I thought that would be really easy to notice on the test, but it wasn't. So a lot of students had a lot of trouble. Now, you could do this another way. So what they're saying here is, okay, let me back it up a bit. Okay, so which segments don't matter at all? I got 1, 2, yeah, 2 and 4. So I'm just going to get rid of those because they don't matter. Why? Because the current either flows radially towards or radially away. Anytime the current goes radially away from this point or radially towards it, it doesn't matter. This one, that's just 1/4 of a circle, piece of cake. Now, do you agree that this segment 1 and 5 are the same? So you could either say, figure out just this one and double it. Or like someone else was saying, you could say, wait, couldn't I just do this as an infinite straight wire? and then subtract out just this portion. And so that's another way you could do it. You could also say, do an infinite straight wire, calculate this portion only, and subtract double that portion. There's many correct ways to do it. And so, but in the end, all you need to do this problem is one straight line segment, either this one and double it, or this one and subtract that one. Excellent. And so you see the types of problems I would like to give you on a quiz with this type of problem. It's something where if you're clever, you can get it down to basically one straight line segment you got to figure out, just so I know that you know how to use that formula properly, and then some circle part, and then you just stick it together in a weird ass shape. Pretty typical. All right, that's kind of the general pattern of all these. And so I'm going to go ahead and leave that one for you to work out at home. There's some details, but I would say this. Let's do one piece of this. Okay, part A. This is the part I saw so many people screw up. I know that this distance is r. I know that this distance, I believe in the problem, is r over 2, right? Wait, this was little r, I think, in this problem. And this distance is r over 2. So you know that we may end up using a straight line segment or something, or let's say we're going to do segment 1, right? That would equal mu naught I over 4 pi sine theta final minus sine theta initial. And I don't know if you could tell, one of these is going to be 45 and one of them is going to be 90, right? So the initial would be negative 90, and then the final would be negative 45. They have the same sign because they're on the same. Or you could just screw it and just stick an absolute value on it. But I forgot something in here. What did I forget? A. Sure thing, eh? Don't you know? So what is A? What does it mean physically? What's the long sentence definition of it?
The distance from the point of interest to the perpendicular bisector.
So where's the perpendicular bisector? If this is my point P,
this is to the straight line segment? I'm sorry.
Yes, to the straight line
Yeah,
segment.
okay.
Which way should I move my marker?
Straight up.
Exactly. And even though there's no wire there, that's the perpendicular bisector. So what is A? Is it R or is it R over 2?
This is for the circle or the line?
This is for segment 1, which is this segment right here, the straight wire.
Still R over 2, isn't it?
It's not R over 2.
My intuition
Well,
would
it's
say
not
neither.
R.
It's
You
not
gave us
R.
you gave
I
us
know.
both, so I'm assuming
was-
you're telling us it was one of those options.
No, I was telling you those to try and trick you because you should know that it's not one of those options.
R over square root 8.
It's this, right? So you got to do Pythagorean theorem. Ah, that's okay. All right. That was supposed to be fun. Sorry if it wasn't. All right. My bad. But the idea is I know that, let's say this side is S. Well, let's see. Or wait, we said this is A, isn't it? So A should be equal to R over 2 divided by square root of 2, I believe. Right? So you could check it this way if you want. You could say, I know that a squared plus a squared should equal R over 2 quantity squared. You could figure it out that way, which tells you you get 2a squared, which then you get a square root, and then you're off to the races. So you could see, even though these are very cookbook problems, the way you get worked over on a quiz is from geometry. All right. And so, and then remember in this particular one, we see a number of factors here. The perpendicular bisector can go to a void in space. If there's no wire there, that's still the perpendicular bisector. 2, you always have to think about this letter A because you always remember mu naught I over 4 pi because it rhymes. Don't forget the A. And then A sometimes is not the same thing as any of the other dimensions. In one of the previous problems, I think A was √2. In another one, it was √2r. Another one, it was 2r. In this one, it's going to be some screwball whatever. All right. Is that good for this question? Making some sense? All right. All right. Just having a little bit of fun here. Let's go on to the next one. This was a test question once. Okay, so we've got these 3 coil designs. Now, rather than do this problem, let's look at it. I'm going to label some segments here. Just give me a second. What do you guys think about the straight line segments in case 1? Are they going to matter to the B field at the dot?
No.
How about the straight line segments in case 2?
Also,
Or-
no.
Yes.
No. Straight towards?
Oh, the straight.
towards?
No, sorry.
Yeah,
I
sorry,
thought you were talking about the other one.
Yeah, so notice these straight line segments. So I designed this problem so that basically people wouldn't have to worry about the straight line segments for this one. So it'd be faster to do a conceptual question. So, okay, everybody's cool. So now we've got this red segment here versus this blue segment here. My question for you is this: will those 2 circular segments produce magnetic field contributions which add together, or will they partially cancel? Or will they totally cancel?
Partially cancel.
Yes. So the idea here is the red one, current's flowing this way, so that produces a contribution which way? Into the page or out of the page at the center?
Out of the page.
What's that?
I would say out.
Should be into the page, right?
Into. Grab that wire or curl the fingers, take the fingers of your right hand and curl it around with that wire right now. And notice your thumb is forced to point into the page. So the fingers on your right hand, curl them in the same direction as the wire, and you can't help it but see your hand pointing into the page. Is that okay on that one?
I don't know if it's just me, but I
Mhm.
always find that using the rule where you point your thumb in the direction of current,
Mhm.
it just seems to work better for me.
If that works, totally good. Yeah. So I tell you what, let's make sure, because you guys can't see me when that's on here. Let's just draw that one case up. All right. So we have it's not perfect, but you get the idea. All right. And so current is flowing this way, and current is flowing that way in the outer. So for this one, you could do this, or like Nick was saying, you just say, put your thumb and say, look, right there, isn't it going into? And that rule works whether it's a circle or a straight wire. So yeah, it's a great rule. This one I like, I don't know why. I guess I grew up that way. So right here, that's, I just forgot, it's into. Okay, so I'll call that B from the inner. Then there's B from the outer, or you could say that one's out. Should it be bigger or smaller? What do you think? The longer wire.
Smaller.
Why is it smaller?
Farther away.
Well, yeah, exactly. So just because there's more wire, the dominant thing is that it's farther away. Good job. You can see I'm trying to be mischievous tonight. So here's the formula, right? For a full circle, mu naught I over 2r. And you say, wait, it's a circle. Shouldn't there be a pi in there? Oh, but physics is hard. Oh, but physics is really hard. There is a pi hidden in the mu naught. Okay. So in this case, we see that the radius of the circle will be larger. And so even if you have the same amount of current, when you add it up over the whole loop, that distance from the source matters more because of an r squared law, right? You could say the perimeter has increased, right? And the perimeter is proportional to r, so the length is proportional to r, but then the equation is proportional to 1 over r squared. You put those two together, you get a 1 over r dependence. All right. Let me show you what I mean. You know, dB is mu naught I over 4 pi times ds vector cross r vector all over r. Oh, let's do this one, r squared. And
Lower
r hat.
the camera just a little bit.
Yeah, sorry, my bad. Like that. And so the idea is the length is essentially proportional to the perimeter, which is some kind of length, has a radius in it. And then you got a radius squared in the basement because they're all points are distant. So we see we get a radius over a radius squared somehow. And there's some other factors, blah, blah, blah. But that's why we get a 1 over r dependence there. All right. So far, so good. Now, what's different about case 2, other than it looks like a spaceship from the movie Heavy Metal from 1980 turned on its side?
Oh, such a good movie.
Lochnar! Suppose a Lochnar is used to create a magnetic field. I don't know. That coffee's really kicking in, people. All right. The whole point of this one is this one, look at those two segments. Let's say we've got the red inner segment and then the blue outer segment. So you can see that these are going to cancel out, right? Or partially cancel out. What do you think?
No, they both go out of the page.
They actually they're both out of the page. And so watch this. If you're inside the loop, both segments will contribute. If you're outside of the loop, one of them adds and one of them subtracts. So notice over here, we get partial cancellation again. So we see that this is a general theme. For points inside of a loop, the segments tend to contribute and add up. For points outside of a loop, the field contributions tend to partially cancel. Got that? That was what that was supposed to be about. All right. Let's see what's next. This one you guys did in lab. It's kind of cool. I hope you enjoyed that video of the car battery connected to two cables. I thought that was kind of neat. This one, we'll probably learn about this during the coding. So what is that? Nate Dogg and Josh actually coded this one up, I think. I don't know who else did that, but so if you're interested, you know when they're talking, you can come see it. Great. This one, okay. Yeah, I think this sums it up. This gets tiresome quickly. Take a guess, then read the solution. So I'm okay with you guys not doing part E on that problem. But what so this actually relates to those of you who did the straight wire coding, then compared it to the lab. So questions 19 or point 13 and point 14, you might be wondering how long is infinitely long? It turns out it's longer than you think. So a ½ meter is not very long compared to 0.1 meters. So you might need to be at least a full 10 times away. And actually, let's look in the solution. I actually worked this one out. So all this time we've been saying, oh, just assume you have infinitely long wires. Give me a sec here.
Is it basically a proportion to how far the particle is away from the wire?
Absolutely.
Okay.
And so it turns out it's 14 times the distance from the wire is what I discovered. So yeah, or said another way, points on a wire more than 7D from the perpendicular bisector would produce negligible contributions at the 1% level, I should say. Now, this is tricky. What if the wire doesn't even go to the perpendicular bisector? Then it's a harder question. But this is just kind of a rule that you can use to estimate. So if I was doing this and I wanted to make an infinitely long wire, I would want it to be probably about 20 times longer than my maximum distance from the wire. And in the magnetic field lab that you guys did, those of you doing option 9, I think it was, you probably noticed that it doesn't match up perfectly. And so, well, when you think about it, there were points where we were 20 centimeters from the wire, and then the length is only 50 centimeters each way. That's only 2.5 times that distance. That means the other segments on that wire are going to contribute and change things significantly. And so that's even true for some of the points that are pretty close to the axis. Now, yeah, we'd have to talk about components and which way and this and that. But the fact remains is, unless you have a really long straight wire, it's not actually very accurate to model it as infinitely long. Okay, so you need very long compared to very short distances. All right, that was the point of that. And then this question right here, I did it because I wanted to do it. This is one I would actually have the solutions up and follow it open. All right, so I'll make you a deal. I think it's very good to learn from, but I'm not going to ask you follow-up questions during your final exam on this problem 29.13. Again, I will not ask you follow-up questions on 29.13. So if you want to, you could mark down in your, basically, I refuse to ask you about this question during your final exam, even though I think I required it. I'm going to check. What is this, chapter 29?
It's not on mine.
Oh, okay. Okay. So this, oh yeah, good. So I remember to say, yeah. So if you want to learn from it, you could see, I did a lot of stuff and you could see where the perpendicular bisectors come in for the different segments. So it might be worth looking over briefly if you want to see how you would deal with a bunch of weird, it's non-trivial to deal with outside of a weird ass loop. But yeah, yeah. Okay. So I'll leave it at that. Okay. 29.16 on page 158. I think it's really cool, but to be honest, unless you have to deal with solenoids in a lab, which I usually have that, but I didn't this year, whatever. 29.17 is a good one. You should definitely make sure you spend some time on that one. 18 is pretty fun. And 29.19 is pretty good as well. Yeah, I'm assuming I told you to do that one, right? Just looking at my list here. Yeah, 17. Okay, yeah. Okay, so it looks like I did a pretty good job picking the problem. I still believe that too. So the problems I told you to do in the list are going to get the job done. 29.20 is going to foreshadow the next chapter, by the way. So if you want, you might be thinking, this seems kind of strange. Just make sure you put a little love into 29.20. All right. And that said, we're ready to talk about magnetic flux now. So I'm done with the BS law. At this point, you can do it. It's just practice, 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 and be ready for most of the next quiz to have Biot-Savart law on it. Okay. So I think there's 4 questions, and I think one of them has Amperes in it, and the other 3 are BS or something. It's been a long time. I can't remember if I did all 4 on BS and only 1 on Amperes, and then plan to focus on Amperes on the final, or if I did just 1 or something. But so you got to know your BS law in and out. Okay. And then you definitely need to know your Amperes law as well. Okay. Let's take a look. So I'm going to now, let's start with a screen share. Those are some fun questions. I think you're going to enjoy that. That said, I now want to talk about magnetic flux. Okay. Magnetic flux. So page 161. Now you might know where this is going. Let's go back to flux. I don't know if you remember, electric flux was the integral of E dot dA. And if you're groaning because you know what's coming, yep, you're right. Okay, so it turns out magnetic flux is the integral of B dot dA. All right, that's cool. Now, earlier we used the electric flux, right? We used this and we said that basically electric flux is equal to Q enclosed over epsilon naught. And that was called Gauss's law. Okay. It turns out Faraday's law looks a little bit like that. It turns out induced voltage, sometimes called EMF, is equal to minus the number of loops times the time derivative of magnetic flux. Oh. Now, it turns out I'm going to show you a lot of tricks on this, and this is in chapter 30. Okay. That said, I'm going to talk a little bit about flux in this chapter briefly. Okay. And then the magnetic flux that I talk about right now, any quiz questions will come in the chapter 30, stuff. So, okay. So if you don't really understand flux in this chapter, you won't get stung on the quiz by flux in this chapter. You'll get stung on it in the next one. Go ahead. Was there a question?
Yeah, could I ask a quick question? What part of this chapter isn't all the stuff we've done so far in 29, isn't it all Biot Savart? Like the Ampere's Ampere's law, that is
Yeah, that's coming next.
Oh, that's coming up. Okay.
Yeah. So now I'm going to do that.
Good.
So so it just turns out I wanted to mention this here. So and in fact, I'm actually going to save this for later, but remember when we did some problems where we did electric flux and then we moved on to Gauss's law. And what I'm saying is it turns out magnetic flux is very similar, but it goes to Faraday's law here. And I guess I was just saying that because that's the order I have it written up. And this is the standard order. You see it in most physics textbooks as well. For some reason, they briefly mention magnetic flux before going into Ampere's law. So now, well, since we mentioned it, let's do it. Let me show you this. Let me get this out of the way now. So Faraday's law, we're going to come back to in the next chapter. All right. There's something about that there. By the way, that picture on top of page 161 goes with problem 29.22. I'm sorry about that. Let me show you what I mean. This picture right here is supposed to go with problem 29.22, okay? Sorry about that. Yeah. Okay. So that said, let's scroll down, see if there was something to be said there. I'm going to let you read this one at home, 29.21. And then this is the one that I was talking about. That figure goes with this problem. I'm going to let you do that at home. And now we're on to Ampere's law problem. And I know that I'm going to come back and hit magnetic flux, something fierce in the next chapter. So now we could talk about Ampere's law. Let me give a brief philosophical discussion of why we care about this. Let's go back to the beginning of the semester. We had point charges, and we said that at this point, P, you could figure out the electric field using Coulomb's law. Right? And then then after that, we said, in special cases, it's a lot easier to do this. A equals Q enclosed over epsilon naught. This was Gauss's law, special. Okay, so what's the equivalent? We know if you have a wire here, you could split this up and figure out the magnetic field from one small contribution is mu naught I over 4 pi A. Oh, well, actually, no, we're doing this one. ds cross r hat over r squared because I used the hat, right? And so we could actually do this. Well, there's an equivalent to this Gauss's law. Special cases, Bs equals mu naught I enclosed. This was Gauss's law. This was Coulomb's law. So we said that Coulomb's law, in certain special cases, it was easier to use Gauss's law. Well, this is the Biot-Savart law. In certain special cases, it's easier to use Ampere's law. This is Ampere's law. Now, I want to point out a couple of things here. Number one, it's only going to work for special cases with lots of symmetry. Remember, Gauss's law only worked for special cases with lots of symmetry. Okay, furthermore, in this case, there are some differences. This is E times area. This is B times S. Let's explore that a little bit more deeply here. So notice there's a one dimension down, 1 dimension of meters down. Okay, so in this case, let's do Gauss's and Ampere's side by side. It was E times area of the Gaussian surface was equal to 1 over epsilon naught times the integral of rho dV. This was the volume of a shell. And this was coulombs per meter cubed. Right? Ampere's looks a little bit different. It would be E, well, oh, not E, oops, B times S of the Amperian loop. And I'll show you some, that's supposed to be a letter S. This would be a length of an Amperian loop. More on that in a second. It's mu naught, basically a physics constant. So it was 1 over, this one's not 1 over. What would be the equivalent way to get current enclosed? What would the integral look like? What did we have to integrate earlier in the semester? Do you remember? What was the density for current? What symbol?
Rho.
That's supposed to be a J. Never mind. J, current density?
Yeah, we barely touched on that.
I know, we did 1 day on it, right? Okay, so who cares? So this is the point. In Gauss's law, we used area and volume. Down here, we're going to use length and area. That's the main difference. Okay, now obviously you don't really understand this until we do some problems, but I have some good news for you. When we were doing Gauss's law, you had to do cylinders, spheres, plates, conductors, and insulators. Blah, 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 blah. It turns out in Ampere's law, while you could do plates, we're going to focus on almost entirely on cylinders. Why? Because wires are usually cylinders, and coaxial cables are cylinders, and nested cylinders. Also, we only have conductors because conductors are carrying current. So instead of having like, what was that? Something like 3 times 2, 6 times something. There's basically only 2 cases. There's solid cylinders and cylindrical shells. And then I guess you have uniform or non-uniform. So the number of cases in Ampere's law is dramatically smaller than in Ampere's law is dramatically smaller than Gauss's law. So with that said, let's maybe take a look at a problem, take a break, come back and do some problems. Or wait, I don't know. Any questions right now? I'm just kind of giving you the big picture here. Let's take a look at a problem. Screw it. Let's do it.
What was J again?
J is called current density. It's amps. Oh, I
Per
forgot to write the
length or-
units. Yeah. So this, sorry, let me clarify here. This is going to be a length of what's called an Amperian loop. Okay. J is current density. Sorry, I forgot to do all this. I said it, but didn't write it. That's a bad thing. And that has units of amps per meter squared. And this is the area, right? And that would be the area through which the current flows. So that's a cross-sectional area. Now, you got to be careful with the A here means amps, and the A there is area. Oh, man. Yeah. So, all right. Did that help out? Is that what you needed, Nick?
And the and the A in the subscript for S. Another A.
Yeah, that means Amperian. Yeah. It's like, oh my goodness. It's just keeping stuff straight. All right. So let's go ahead and start the next one. Now, it's the next problem. Let's do the next problem in its entirety, then take our break. So we are looking at, problem is that 29.23, page 164. If you don't want to listen to me and just want to work with the solutions, do it. If you want me to do it for you and you can read the solutions later and you just follow along, that's cool. Whatever works for you. So here we go. (29.23). Okay, we have a solid wire here. We're looking at a cross section of it. Remember in Gauss's law, we were always looking at cross sections? That still holds true. We're told that this one has some radius, big R. That again, huh? Now we're outside the loop. So again, what does this look like? This is a wire that's coming out here forever, and I'm just doing a loop around here. It's like I'm walking around just in one plane like this. Well, basically this plane. So the idea is this wire extends forever in both directions, okay? It's infinitely long, or at least 20 times any distance we care about.
Does this work for only a perfectly straight wire, or can it work if it's curved?
So technically the formula would work for anyone, but it's almost impossible to calculate it if it's not infinitely long and straight.
Okay.
Yep. Now there's some weird exceptions that I'll get to at the end. So I want to point out this radius I'm going to call little r. So notice little r is bigger than big R in this case. So we're outside the wire, And, you know, we could say all kinds of things about this. Well, let's do it. For this first problem, I'm going to point out which way is the magnetic field pointing? Does it say which way current flows? Into the page. So in this problem, current is flowing into the page. Based on that, what direction is B at this point right here?
Down.
Down.
Yeah, and do you agree it's going to curl around here? Just like the compasses in some video that maybe you didn't get to watch? So there's the B field. Now, strictly speaking, this is the correct way to do it. We'd say that the integral along a closed, the integral along a closed path of B dot ds should equal mu naught I enclosed. Okay. Well, in this case, do you agree that B is always pointing the same way as ds? If you're going around this circle in this direction, they're always pointing the same way. What should happen to the dot product?
It drops out.
Yep. And so this just becomes straight BDS.
So
Go ahead.
maybe I'm reading this wrong or something, but I know, so like it is true that the current is running into the page, but
Yes.
but then you say like 2 sentences later, assume that a uniformly distributed current runs out of the page.
Oh, whoops. So I just
You just doubled up just for
yeah,
like, I don't know, your mistake.
it's not gonna
log or
matter.
whatever.
It's not gonna matter.
Yeah.
Yeah. So sorry about that. Let me double check. Where you said? Let's see.
It was just at the beginning of 2923.
Oh
problem
God.
statement.
So I should have said yeah, I guess I should have said out of the page or into the page. Just one of them. I just screwed up. So
Okay.
thanks for pointing that out. Maybe yeah, I'll fix that later. But yeah, thank you for pointing that out. I just screwed up. All right, so for this problem, it doesn't matter which way, because in the end, we're only going to get the field magnitude, so I'm safe. Whew. All right. But now in this case, if we do assume it's going into and going around this way, sorry about that, that gives us this. All right, this is mu naught I enclosed. Thank you, T. All right, now, why is it okay to take this magnetic field out of the integral? What's true about all these arrows?
They're constant, or they're not constant. Oh, they're constant. I mean,
Constant.
They're each going to have an equal and opposite one across from each other.
Constant magnitude. They're not constant vectors, but constant in magnitude. Well, this is the magnitude because we took care of the vector with the dot product. Got it? Yeah. And this is why this is only going to work with basically infinitely long stuff. So Nick, I think, asked, would this work if it was curving? This statement, we wouldn't be able to do these tricks if it was curving around. So then we couldn't do this trick. Well, B times the integral around a closed loop of ds is straight up just the length. Okay, well, what's the length? Who was the roundest knight at King Arthur's table?
Circumference.
Circumference. Is it 2 pi big R?
Little r.
By small r.
Little r, little r. All right, all right, all right. Okay, this is equal to mu naught. How much current is enclosed?
All of it.
All of it. Wait a minute. You just told me that the magnetic field magnitude is what? Mu naught I over 2 pi r. Isn't that a lot easier than the Biot-Savart law? Of course, now that we have that memorized, but so we're just trying to show that we get the same result as we would have had we done Biot-Savart law. Go ahead.
So at the beginning, the ds, right? Isn't that the way? That's the direction of.
It's going along the loop. And so if I'm traversing, it's an arc length along the way you travel around the loop. And so if you choose to travel around the loop in the same direction as the B field, these
Then it
two will
just
always give you
divides the dot
BS.
product. Okay, yeah.
And so going back to Nick's question, the only time we ever use this method is when we can do this shortcut. Otherwise, it's too frickin' hard and it's no fun. But it always works, technically. It's just sometimes this can be extremely difficult to calculate. Doing a dot product before it gets the integral becomes so much more difficult. All right. Well, that's part A. Let's look at part B. We're going inside the wire. Or whatever it says. Okay. So now Okay, so there's our wire. That distance is capital R. And now what I want to do is I don't want to enclose all of it. I just want to enclose some of it. So now we're doing little r less than big R. Okay. I know from experience by symmetry, because there's so much symmetry here, rather than do that long process again, I can start with this. B times the length around the loop, which is 2 pi r, should equal mu naught I enclosed. Again, the same logic I used in the previous problem would get us all the way down where this is B times the length of the Amperian loop. This is S equals length of Amperian loop. Amperian loop just means the dotted red line. It's the loop that I drew to enclose some of the current. Well, how do I get I enclosed? Let's do it the general way, then I'll show you the shortcut. In general, the method that works all the time, whether it's uniform or non-uniform, it's always going to be the integral of j dot dA. Now, nobody likes vector calculus if we can avoid it. I want to point out this one, for whatever reason, we chose to assume the current was going into the page, right? Now, was this particular problem uniform or non-uniform? Did it say uniform current distribution or non-uniform current? Uniform. Somewhere in there it said uniform way in there, all right? How do I get current density if it's uniform here? Oh, let's do the vector part. J, in this case, I don't know if you could tell, but J would be into the page. The current density vector points in the direction current flows. So in this case, it would be negative k hat. Which way do area vectors point? Do they point in the plane or perpendicular to the plane?
Perpendicular.
Perpendicular. So that's also into. So to be clear, that's an area, right? The red area here relates to this thing. Actually, we're going to split this up and build up that area out of small rings, right? And so the idea is what we're going to try and do is get the total amount of current flowing through that red shaded area. So we want this, the current that's flowing through this entire area right here. And to do that, what we're going to do is we're going to integrate over rings that build up this one. So notice this ring area right here, this one points in the negative k hat. This one points in the negative k hat. And if that's the case, I can get rid of this dot product, and that will always be true for these problems. So we can actually simplify this to just j dA without the vectors. I'm going to pause, and that's not that important of a step. All that really matters is that you know this is what you need to work with. If you're curious how we get to that, and if you were wondering that, oh, isn't that a vector? Well, there you go. I explained it. But this is what matters. Now, J, if it's uniform, does anybody remember the formula? I'll give you a hint. It was units of amps per meter squared.
Current over area.
Yes, if it's uniform, it's going to be I total over area total. Okay, which in this case, what's the total area?
Pi big R squared.
Pi big R squared. What's dA? That's this area right here. What's that area going to be?
Pi d R tilde.
On the right track, it's all the way around times the thickness. What's all the way around?
2 pi r.
And then the
dr.
thickness. Okay. And then you're off to the races. So at this point, let's actually plug this all in. So I just want to point out, here's our current density. If it's uniform, you can figure out the current density. If it's a non-uniform problem, oh, great, I have to use the formula he gave me. So when I do all this, I'm going to plug this in. I enclosed is equal to, it was the current density, which was I total over area total. Okay. And then I have times dA, which is 2 pi r twiddle dr twiddle. Now, this is a constant and it pops right out. All right? Big R is not changing. R twiddle is changing. Little r is, yeah, that's the Gaussian. That's not changing for this step. So basically, R twiddle is the only thing that's changing. So in this case, I'm going to actually, you might cancel the pi's here, but just humor me and don't. I just want to show you because it'll make it easier to see a shortcut later. Now, when I integrate this, I'm going to get a pi r twiddle squared over 2, right? Oh, but the 2 cancels. And now I need my limits. What are my limits for this case? What's the smallest shell? What's the smallest green shell I would use?
0.
0. And what's the largest?
Big R.
Nope.
Oh,
Little
little
R.
R. You switched
Yeah,
it from
so
last time.
because remember, now we're
yeah,
inside.
now it's
Yep.
inside.
And so remember, if it was big R, we wouldn't even waste our time with this because you just know the answer is I for I enclosed. So that's the kind of trick is usually, okay, there we go. Good job. So now this goes from 0 to R, and I just want to point this out. Current enclosed is I, and then I notice there's a pi.
Can you move the screen down a little bit, please?
Thank you.
Thank you.
Yep, thank you. All right, so here in this case, sorry, let me go back here. I enclosed is JDA. J is I over pi r squared because it was uniform. It's total current over total area. dA is the area of this stupid little shell. Well, that's 2 pi r, the distance around, times its thickness. When I integrate that, I'm going to get this crap here. There's a pi r squared here. And notice in the end, I get pi little r squared. Or if uniform, the current enclosed is current total times Amperian area over total area. Remember that trick in Gauss's law? It was Gaussian volume over total volume, but now we're in Ampere's law land, where we use areas on this side and lengths. So Gauss's law, we always used areas and volumes. Now we're always using lengths and areas. What do you think? I have no idea. I might have been going way too fast. Thoughts, questions?
So you said the top one was the not Gaussian, Amperian area, and the bottom was the total area.
Yes, so we see
Okay.
it's Amperian area over total.
And this case works for all of these infinite long ones,
Yep.
the wires? Okay.
And this works. Why this is really nice is this helps us figure out the magnetic field inside of coaxial cables. Now, why would you care about that? Because it helps us figure out the inductance in coaxial cables. Why would you care about that? It helps us figure out how it's going to affect the signal when you try to send us a radio frequency to somebody. So all this is actually useful somewhere way down the line in like a chapter or two. All right. So at first you're like, this is fucking stupid. But in reality, it's extremely useful to help us understand how wires and cables work and why certain signals from the TV or radio are causing noise. And if you become a scientist of any import, you're going to have to deal with noise all the time. And what you're always trying to do in a real life lab is get better signal and less noise so that you can get your measurements done quickly and go home. All right. So it turns out this relates to that. All right. So there is some just like before, we were doing a bunch of pie in the sky math and you thought it had nothing to do with it. And then, whoa, we got to circuits. We got one more chapter of pie in the sky math. And then, whoa, we're doing AC circuits. All right. So it's going to come back together to circuits and finish the semester. Yeah, good. Other questions?
Wait. Did you say something about finishing the semester?
Oh, that's right. You guys can drop. That's cool. Just drop before I have to listen to your talks. Damn it. Oh, man. Yeah, my least favorite thing is people that go through all this work to do a talk and then drop right after. I'm like, oh, man, you did all that work for nothing, man. That's all right. You still learn, right? So, all right. It's time to take our break, but because we're in this question, let's just look at it really quick. See if there's, okay, so I know I'm going really fast. I'm just trying to give you a feeling for this. But let's take a look at this problem here. Where is it? Gosh, this stuff would look like space gibberish if you didn't know what we were doing, huh? There we go.
My son walks in all the time and says, that's giving me a headache.
Yeah, right. Okay, so here we go. This one, I think you guys kind of followed that one, not too bad. And then, okay, notice I threw the magnetic field vector back on. Okay, blah, 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 case 2. So there's that one. We kind of talked about this. So I walked it through better in the notes than I did on the board, probably. Oh, here's some things to do. Check the units. So I don't know if you've noticed this. Our classic formula is mu naught I over 2 pi r, right? So rather than check the units correctly, we know this magnetic field is for a long straight wire. Notice the mu naught's on top, I is on top, meters on bottom. So when I look at this, mu naught on top, I is on top, meters on bottom. And then the other thing, notice the two formulas match when little r equals big R. That's a way to check this. Okay. I'll pause. Any questions about checking the units? It's basically like before we used to make sure K is on top, Q is on top, meters squared on bottom. For magnetic fields, it's mu naught on top, I on top, R on bottom. Let's go to the next page. So what would I do next? Plot it. Remember the trick for these ones. Here's the tip. You do these things. You just, if you want to plot them, do that. Okay, good to go. And then this gives you an idea of what the magnetic field looks like. So if you want, you could redo this problem right after class and see if that makes sense. It's 5:55. Let's go ahead and take a break. I think that's that whole problem. But I do want to, I guess I should point out this. Notice it rises linearly. So you get some kind of, or you could say it's proportional to radius. Whereas here, it's proportional to 1 over r. That's not an alpha, that's a is proportional to. And so this 1 over r dependence gives us an idea why you have to have such long wires. Perhaps you know that in calculus, 1 over r doesn't converge, right? And so that's why magnetic fields persist much farther than electric fields did for the same kind of shape. Yeah, go ahead.
At 1, is that where big R is equal to little r?
Yeah, so this is...
Oh, okay. So that's, so the linear part, that's where it's inside the actual
This would be
wire.
inside.
Okay.
Yep. And then right here's the transition, because at this point, this is where little r equals big R. So this, so yeah. Does that make sense?
Yep.
Nice, nice. Okay. And so, all right, let's call that good. And yeah, if it helps, you can kind of see this down here. Whoops. We see the field ramps up linearly and then falls off slowly as 1 over r. And that's why it persists so far outside the cable. All right. Another thing that happens, if you have a beam of ions, which can happen, like some of the lab groups had ion beams, you could actually view the ion beam as having a non-uniform current density. So people that use beam physics, actually, this relates to what they do, and their current densities usually have a Gaussian curve in them. By that, I mean e to the negative x minus mu over sigma quantity squared, something like that. Let's take that break. You guys are cooked, I'm sure. Let's take a quick break. You take your break as long as you want. Just if you take it till forever, make sure you drop. Yeah, eat something. I don't care if you eat during my class. I have no idea if this is working for you guys at all tonight. I feel like I'm going really fast, but is this going too fast for you guys, or are you getting something out of it, or is it hard to tell?
I think it's fine so far.
To previous sections that it doesn't feel like completely new. It's not too bad.
That's what I was hoping, is that maybe, you know, the more we do it, it kind of, the muscle memory kind of comes back or whatever. Maybe after we do 2-3 more of these, then you'll be in a spot where you can read and be like, okay, let's fill in the gaps that I'm missing. Because I'm sure there's just so much in these problems, right? All right. So I'm going to actually, how long have we taken? Was that 5 minutes, 10 minutes, something like that? I think it was about that.
It was 10 minutes, I think.
Yeah, I think I stopped at 5:55, but then I said a couple more things. So I'll do kind of a slow start. So right now, what I'm looking at, if you look at page 166 in your workbook, these are in the solutions, the same shit in color. Okay, so if you want to bring up the solutions to chapter 29 and follow along, you can do that, but I'll have them up on your screen. If you want to just look at the workbook, I just want to point out, here's kind of like all the guts here. So let's focus on cylindrical symmetry, so wires, and let's maybe look at these kinds of things. So let's say you have a uniform wire and you're outside the shell. Well, we know that B times S, we're now using S on the left side instead of area, is the distance around is 2 pi r. Current enclosed is all of it. So we get the exact same result for a cylindrical shell as we do for a solid wire. Shocking. What if we're inside the shell? If we're inside the shell, now I want to be clear, we're talking uniform. Okay, uniform. Oh, whoops, there it is. Uniform inside a shell. Well, in that case, it's BS is mu naught enclosed. S is still 2 pi r. That's the distance around the loop. And now we'll just have some of it. Because it's an Amperian loop, it's the total area and the Amperian area. And then notice there's the current right there. So it's the ratio of this red area to the full area. Now in this case, it's going to be pi radius outer, and we're only going out to little r. Only going out to little r, minus pi inner radius squared over the whole area of the shell. So I'm going to pause there and see if that example makes some sense, or if you have any questions about the math on the right side. I'm going to actually wait a second just in case. That's the shortcut trick.
And so that's the magnitude, obviously. So then if you were going to do the
Absolutely.
direction, that would be in, like the direction of it would be
Right-hand rule, either this
with
way
the
or
same
that way.
thing.
If
Rolling.
current's coming out, you would do this move. And the B field would be either theta hat or negative theta hat.
Cool. Okay. Sweet.
Is that good?
That makes sense. Yep. Thank you.
Yep. So you're going to see a lot of theta hats in this section, meaning either basically clockwise or counterclockwise, whichever. Yeah. Okay. Oops. Wait a second. Something looked a little funky there. All right. So let's, other questions on this one, or is that one kind of making some sense? What should you check with every calculation?
Units.
How will we check the units? Mu naught up top, I up top. What do I need on bottom? What units on bottom?
Meters.
Meters. Because remember, just go back to one formula that you have memorized. Mu naught I over 2 pi r for the long straight wire, right? And so notice I kind of grouped this like that so you could see it. It's just like the straight wire, but then we take this ratio that has no units. Everything in there has meters squared, so they cancel out. So I have mu naught on top, I on top, r on bottom. What else should you check with an Ampere's law problem? Do you remember? We did outside, we did inside. You can always check.
Where little r meets big R.
Yeah, so let's plug in little r equals big R. Now in this case, what's the big R, I guess?
B.
B. So this one is mu naught I over 2 pi b when we get to the boundary layer. So when I get to the boundary, they should have the same result. This one up top just gives me mu naught I over b. Let's look at this one. If I plug in b squared here, this becomes 1, and I get mu naught I over b. It matches. The units check. We see that at the interface, where we change from inside the shell to outside the shell. Great. Wait a minute, people. What's the B field right here where I'm drawing a blue dot?
Zero.
Why?
Because there's nothing enclosed.
Boom. There we go. Got it? Remember, so if you're inside the inner shell, no current enclosed, no B field. Sweet. All right, let's move on. Let's take a look at this. What if we have a non-uniform and you're outside the shell, and for some reason I just made the craziest one I could think of. Let's say the current density is given by alpha r to the 7th. Strictly speaking, I should be saying the current density magnitude, but whatever. All right, so let's take a look at this. You can see it gets a little harder. I'm going to pause and see what you think of this. So you can ask me questions about any piece. I start over here. Whoops, let me get my annotator ready. I usually start on this part. First thing I do is I say, okay, I might as well get the total current. I'm figuring out a relationship between total current and the constant. Notice that? I'm getting a relationship between total current and the constants. And when I do that, I solve that final relationship for that constant. That way, later on, if a constant appears in my equation, I can get rid of it and write this thing in terms of I total. Let me see here. So again, this was just some random thing I give you. We plug it in. You got a lower limit and an upper limit. This is the standard shell. That's the green shell area. So this shell area right here, that shell has this area. There's my density, and notice I change it to R twiddle because I want the current density at this particular radius times the area at that particular radius, and then I'm going to do all of those. And then in this case, because I'm doing the total current, I'm going to use the total limits from A to all the way out to B. Let's keep plugging along. So I factor out the constants, I do the integration, and then I just rearrange it for alpha. So hopefully that part on the left is okay. Now what do? I come over here to this side. If I want to get the magnetic field outside, BS, well, that's always 2 pi r. We see that just dropping all the way down there. Okay, got it. Now, in this case, I have all of it. Well, all of it, that's what I just did right here. I total, right? So I just keep following down. You don't need to do this integral again, but I did it. You could have just grabbed this I total and shoved it in right there, right? There's the 9. There it is. Now, I want to point this out. While not required, sometimes it makes a lot of sense to do this. If you take alpha and plug in what we know, it's a lot easier to see, doesn't that look like a pretty reasonable result there at the bottom? Notice a non-uniform wire is also exactly the same as a uniform wire, whether it's a shell or not a shell. You could set A equal to 0 if you wanted. So we see that no matter what kind of current density you have inside of there, uniform or non-uniform, as long as the current density is radially distributed, as long as it varies along the radius and not along the angle, we expect that you're always going to get outside of the wire. It's always just mu naught I total over 2 pi little r, where little r is the distance from the wire. Now, if you go down here, the main difference in here, notice the upper limit, right? So if you're inside, trying to compare and contrast here, if you're outside, you do the total A to B. If you're inside, we only go up to little r because we're only looking at some of the area up to little r. Hopefully this is seeming vaguely familiar now. Okay. When I go down here just a little bit more, there I get this crazy looking answer. Oops, I get this crazy looking answer. And again, I eliminate alpha using this stupid thing that we figured out from the left column. Plug it all in, and notice I get this crazy looking result. How do I check it?
Match up the radiuses and get something reasonable.
And does it look good? If we put it in here, if I put in radius B, so they should match when I get to the edge, right? The outside formula should match the inside formula when I get to the edge. Well, the outside formula, if I'm at the edge, I just plug in a B. This one, if I plug in a B, it almost gets so easy. You're like, wait a minute. How did I have so much trouble with Gauss's law? Well, because you were learning back then. But yeah, I don't know. I mean, after you do enough of these, you're like, wait a minute, this is just a pattern. And I hope at first you may not notice it with Gauss's law because you're drinking from the fire hose. But at this point, you're like, wait a minute, this is all just kind of straightforward stuff, I hope. Notice what's the other way you could check it? We check that it matches. We should also check the
units.
Units, mu naught on top, I on top, meters on bottom. All this stuff cancels out, done. What do you think? Is that making a little bit of sense? Kind of, those are complicated worked examples. So you could basically, everything after this is going to be modeled off that. So on your final exam, I'm not going to do anything with slabs, but yeah, let me see if there's. Yeah, that's pretty much it. Let me see. Let me keep going in the workbook now. So we kind of done a couple of these. You could imagine on your final exam, I might give you one of these Ampere's law and make you make the plot because you haven't had to sketch the plot yet. So we'll see if I stick. Look at this. Here's shells. The same kind of, oh, yowza. Let's look at this problem. Page 169. Take a look at it. Okay, we're on page 169. You got nested cylindrical shells. You got radii A, 2A, 3A, 4A. I feel like I should make a joke about maybe taking a foray into a foray into the world of magnetic fields, but it's not going to happen. I guess it already did. Assume that in the inner shell current runs into and the outer shell current runs out of. Determine blah, blah, blah. Okay, before we go on, which regions have no magnetic field? Are there any? If I label them, that might make this easier. Let's call this region 1, region 2, region 3, region 4, region 5. Are there any regions that have no magnetic field?
Region 1.
Okay, that's part of it. What other regions or region? Sneaky, isn't it?
Would it be 5?
What? There we go, Sam. Nice job. Why is it 5 and 1?
Are you asking me?
Sure, Sam, go for it.
Oh, because I saw that for one, it says current runs into the page and the other one's out of.
So what's
That was my philosophy.
Yeah, you're absolutely right. So remember, the magnitude of those fields doesn't cancel, but we know that outside it's a vector. So this one, if I call this region 2, B2 would be a field this way. B2 would go this way. And then B4 would go this way. And then another way to think about it is you have some I going into the page and some I going out. Even though I is not a vector, the net current is effectively 0. If you have 6 amps flowing towards me and 6 amps flowing away from me, that's equivalent to 0 amps.
Does the distance away not matter?
No, and isn't that cool? Let me show you here on the board. So that's a shock. So gee, I wonder why people use coaxial cables now. It's because if you run current down the middle and then back on the outer shell, you have no stray magnetic field outside the cable.
So the current, because the current, but the current density obviously is different due to the fact that it's different radius.
Yes.
But
Ampere's law holds.
But the current's the same. So then what if you give us, like, could there be one where you said, like, find out blah, 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 if current density is the same for both of them? And then, like,
I don't know. So almost certainly yes.
Yeah.
And that's one of the other practice problems I just skipped over. But so I just want to point out, let's think about this. If we do these two things separately, if you viewed these two separately, you know that outside of this one, B is, let's call this B2, is mu naught I over 2 pi r. And then because this one was, Sam, what was it? Was the inner one into? Is that right? I think.
Yeah, it's into.
So now which way is this one going to cause a magnetic field if I'm up here? This way? I think, right? So into the page, it's there. And when you're outside of a single shell, it acts like a straight wire that's solid, or yeah, who cares? So I'm going to call that one negative theta hat. Just because the standard math direction, this way is theta hat, and that's negative theta hat. Okay. So now I've basically taken this magnitude that we know from Ampere's law and turned it into a vector. Now look at this one. Well, let's do this one in a different color. Okay, the same thing holds here. Before is mu naught I over 2 pi little r. So if I'm sitting up here, it's the same distance away. It's the same distance r because they're concentric. Okay. So now at this point, I could then upgrade this to a vector. Well, in this case, if I want to make it a vector, this one would be this way. So it would be positive theta hat. if the current size is the same, if current is the same, and if the distance from the center of each shell is the same, when you add together the vectors, boop, boop, it drops out. Crazy. All right.
Wait, why is R the same again? I don't know if I was gone.
It was because these two wires were concentric in the problem statement. Let me show you what I mean. So what I'm saying here is, let's say I want to learn about the magnetic field at this spot that I drew. Okay. I know that all the distances are defined from the same center. So it would be the same whether I use this blue shell or this green shell, because the distances are determined from the center of each shell in all these formula.
Okay, I see.
Is that okay? Yeah. And now where this gets crazy is if they're off center, then everything I just said is false. So for example, if you did this, and then this one was over here, it's not symmetrical anymore. So if you tried to add this shell and this shell, you could use Ampere's law for each shell separately. Okay. And then what you'd have to do is you'd have to draw one coordinate system for this one, another coordinate system for that one, and then do a coordinate shift on the theta hats to blah, 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 blah. If you're a beam physicist, you might have to do that. I just noticed the desire and beam physicist took a, like I could feel the force weakening there. All right. All right. Oh my gosh, I'm losing it. All right. I should rephrase. I lost it a long time ago. All right. Hey, here's a couple of things that aren't on the test. I'm going to say that again. This is page 170. Here's a couple of things that aren't on the test. Solenoids and doubly wound versus singly wound and toroids. Now, you may be wondering why I'm saying anything about them if they're not on the test. It's because these objects are hugely useful in the real world. So if you're an engineer and you need to get a magnetic field, a lot of times you reach for a solenoid or a toroid. Okay. So don't stress out about learning these, but just know some interesting stuff about them. So let's take a look at them really quick. Boring. All right. There's Ampere's law. You know what? I think this is the good statement. I like to think of the air core solenoid as the magnetic equivalent of parallel plates. So parallel plates create constant electric fields. An air core solenoid gives you a constant magnetic field. So it's basically the air core solenoid where you do a bunch of these is even better than the Helmholtz coil. Those of you that know what a Helmholtz coil is, great. Those of you that don't, you're going to learn about it on Tuesday when some groups give a talk about it. So I guarantee you'll learn later. So Helmholtz coils are really nice, and I'm going to let them explain why. They have their own special things, but solenoids are also really nice. Think about it. Maybe you've seen a picture of an MRI. What object do they shove you inside of to do an MRI?
A hole.
A solenoid. The hole is surrounded by superconducting coils that have massive current, so you get a large uniform magnetic field. So if you've ever had an MRI or know somebody that's got to do an MRI, they use a solenoid. Has anybody ever done any automotive work and knows what a solenoid is in a car? What's a solenoid in a car? Somebody knows more about cars than me.
Your alternator?
Yeah. So what is it? It's in your starter contact points. There's a solenoid or something, right? I don't know.
Yeah.
But yeah, so solenoids are used in your car. So if you want, you could look that up, and you could tell I don't fix a lot of cars, right? Yeah, I just break axles.
Actuate a pin with it.
Yeah, so
backwards.
I guess let me put it like this. A solenoid is really cool because what you could do is you can run current through a solenoid and turn it on and create a large magnetic field, large. And that can cause something to move, which is what he was talking about, move an actuator pin. So in this case, you could also use them for relays. So a relay is basically a switch that can be turned on or off from a distance by a solenoid. So yeah, these are hugely used in practical applications. The toroid, so there's some physics about it. I'll let you read about that. Great. There's different ways to wind solenoids. I'll mention it like this. It's oftentimes very advantageous to wind your solenoids like this. Why is that? Let's say you have current flowing in and you wind it singly and then spit it out. Well, you still have some stray magnetic field. Whereas in this one, if you come in on this pipe and come out on that pipe and you wind all the way up and then wind all the way back down, you reduce the stray magnetic field significantly outside of there. So a lot of solenoids are going to look like little cans like this. And then you have a whole bunch of wires wrapped around them like that. Okay. So, yeah. And finally, let's talk about toroids here. The toroid, it's actually really straightforward to get this one, and it's kind of cool, but it's not on the test. So you've got a tasty looking donut. These are useful for making inductors. So it turns out an inductor is an object which actually resists changes to current flow. So just like a capacitor resists changes to voltage, a toroid or an inductor can resist changes to current flow. And more on that in another chapter or two. So those are the solenoids and toroids are the practical shapes used to create large inductances, which is it's basically like current's inertia. All right. We're almost done. Give me a sec here. Hey, blank. We did it. We made it through this chapter. Oh, yeah. So we'll come back and do magnetic flux next time. So I'm going to stop there. If you want to take off, take off. If you want to ask questions, that's cool. There's my kids sneaking in. Girls, what do you know about physics?
Investing $667. And what was my other thing? Oh yeah, I also know how to do coding.
There you go. Okay, that's enough, girls. Okay, get lost.